Hey everyone, and welcome to today's video. Now we are going to go through the 2024 paper for probability distributions for level 3. We're going to go through all the questions, so make sure you've got your calculator and a piece of paper and a pen ready, because the best way for you to benefit from this video is to pause the questions, do them yourself, and then watch us do it together if you didn't know how to do it. A person's belly button can be described as an innie or an outie, as pictured below. Well, unfortunately, there's no picture. Sorry, guys. Belly button shape is a cosmetic characteristic and not a significant indicator of health. So data about belly buttons is not routinely collected. It is therefore difficult to make a reliable estimate of the proportion of outie belly buttons in the population. Data on belly button type was collected in the world's first belly button survey. From this data, it was found that 96% of respondents had an innie belly button. So let's have a look what we need to do. Using an appropriate distribution model, calculate an estimate for the probability that in a class of 30 students, no students have an outie belly button. State the probability distribution model and parameters as part of the answer. So when you guys do these kind of questions, the first thing I always want you guys to do is write down the probability distribution. So if you guys are looking at this question here, the first thing I always want you guys to do is to think about what the probability distribution is. So we're going to write down X here is distribution, and now we have to figure this one out. So remember, go through all the probability distributions that you know and have a look which ones work. The question here is giving us that we have 30 students available, so we have a number, and we also know a probability here. So if you guys have a look through all your probability distribution models, there's only one that fits this. Yeah. So we have n, which is 30. That's the number of students. And we have a probability for each student, which is a 96% for a innie belly button. So if you have got a number and a probability, the only probability distribution here is binomial. And that, of course, fits really well because each of the 30 students has its own probability, or in this case, hopefully the same, right? 96% of having an innie belly button. Now we're going to write X has distribution, and then we're going to write binomial. And we're going to have to give the parameters. And remember, if you go to your formula sheet, you can go to the binomial distribution and it will tell you what the parameters are. So in this case, n is a parameter and also the little pi that they have. Yeah, so in the formula sheet, the probability is actually a little pi. So if you list both of those, then we're already done with the first part. N is 30, so that's 30 students, and the probability of an innie is 0.96. Now let's have a look at what the question actually wants from us. So the question wants the probability that in a class of 30, no students have an outie. Yeah, so this is what we actually want. So we want the probability of no outie. So what does that mean? That means that we have everyone has an innie, right? And the reason why we want to change this is because we have our probability for the innie. So what are we going to do? We're going to put this into the calculator. We want the probability that X, in this case here, yeah, is equal to 30. We want 30 students to be able to have the innie. Yeah, so let's go to our calculator and let's put that in. So how do we do this? Well, remember, we're going to go to the stats menu. So we're going to go to stats and we need to go to distribution, which is F5. And then we have to look at the bottom here. We have binomial, which is 5 again. And remember, guys, if you have a equal sign in the probability statement, then we use BPD. Yeah, and if there is a less than equal sign, that would be the BCD option. So let's go to BPD, which is F1, and make sure that the first one is always on variable. If your one says list after a reset in the exam, make sure you always go back and change it to variable. And it will tell you what you have to put in. So the x value here is, as we have 30. The num trial, that's our n value, that is 30, sorry. We have 30 again. And the p is the probability of success. So that is, in our case, 0.96. Okay, let's press enter. And our probability is given to us by our calculator, which is 0.2939. Remember, guys, 4 decimal places for probabilities is expected. Awesome, wonderful. Now where we've got this, getting this answer will give you guys an achieved mark. Yeah, you guys have to both find the probability as well as stating what probability distribution we have. Okay, let's have a look at the next question. If you need extra support with your studying, join our free Discord community where you can ask questions, get help, and even request me directly for one-on-one tutoring. Inside the Discord, you'll also find a full resource hub with worksheets, study guides across different subjects, and I highly recommend checking out my website where I've put together full courses organized in order so you won't miss any of the topics. You'll find both links to the Discord and the full courses right below in the description. And here it says give 2 reasons why the use of probability distribution model selected in part 1 is appropriate. And now there's more options here. Yeah, so there's a lot of options that you guys can choose from. But usually when they ask you to give reasons for a probability distribution, what they really want from you is that you tell them that we have the parameters, yeah, that we are satisfying, as well as the conditions. Yeah, so if you guys remember, the binomial distribution has several parts that we need to fulfill. So for example, we want independence. Yeah, they want independence for each trial. The next one that we want is we want the same probability. Sorry about my spelling. The same probability of success. That means that every time we choose someone, they have the same probability of having that inner belly button again. That doesn't change. Yeah, we have independence and the same. Now, what else do we have? Yeah, so we have that all of the outcomes are possible. Yeah, another one is that we have a fixed number of trials. Yeah, and that is the case. We have 30 people here. Yeah, we always need a fixed number. That is a requirement for our parameter, for n. Yeah, this is the n parameter. Sorry, I should make it n equals 30 in this case. Yeah, and the same probability of success, that is our pi. Yeah, sorry, I'm just getting just about in the corner over here. One more thing for the binomial distribution is that there are only 2 possible outcomes. So what do I mean by that? Well, we can have an inner or an outer belly button. Yeah, we can't have something completely different. We can't have no belly button. Yeah, it is actually possible to have no belly button. People are born with no belly button, or not born, but they may not have a belly button. And therefore, this would not be quite right here. But in this situation, to justify the probability distribution model, we have to have just 2 outcomes. Any of those answers here will give you the marks. Yeah, so if you guys have 1, this will be an achieved mark. And if you guys get both, then you get a merit mark. But here you have to also get the probability distribution and the parameters in the previous question correct if you want to get a merit for this question. Awesome. Let's have a look at the next question. Belly button fluff is the accumulation of fibers, lint, or debris that collects in a person's belly button. A belly button survey found that 66% of all the respondents had fluff in their belly buttons. Using an appropriate probability distribution model, calculate an estimate for the probability that 1 student in a class of 30 has an outie belly button and it contains belly button fluff. So let's quickly mark this. So we have 1 student in a class of 30 has an outie belly button
and it contains belly button fluff. Okay, this is what we're looking for here, right? You should state the probability distribution model and the parameters used for your answer. So again, we're going to tell everything that we want. So now we want an outie. Yeah, we already know this from the previous one. Here, X has distribution binomial. Again, binomial. Yeah, we have two outcomes. We have the same probability of success each time, and we have 30 students. And now we want to have a look. What is the probability of success here? The probability of success is now an outie belly button because we want an outie belly button. What is the probability of the outie? Well, we know that for the inner or innie or whatever it was called, sorry guys, we can scroll back real quick, was 96%. Yeah, so the innie belly button is 96%. So then we have that the outie belly button is going to be 4%. And I'm just going to make this as a decimal here. Yeah, so 0.04. Remember that you do 1 minus 96%. Yeah, is your 4%. Yeah, why can we do 1 minus? Because these are opposites of each other. Yeah, they complement each other and make a whole. So once we have our probability distribution written down with the parameters, always remember we want the parameters. Yeah, get into the habit of writing those down. We now want to find the actual probability. So first of all, here the belly button type, yeah, is independent to the belly button fluff. At least this is what we assume here. So you can kind of think of this as a probability tree, yeah, where we have first we have the type and then we have the fluff. So we can either be of type inner or outer, and then depending on each, we can have yes or no for fluff. So if we now have a look here, what we're interested in here is we want an outie belly button and we want belly button fluff as well. So how do we now do this? Well, we need to have a look at the probability of being an outie. Yeah, we want one student to be this, and we can use this for the probability where X is equal to 1. Yeah, so remember we want one person to be an outie. So let's quickly go to our calculator and let's put this in. We already have everything set to the right numbers except from the probability itself. So we're going to have to change this to 0.04. And now what we're interested in is one person. So we're going to get 36.7%. So we're going to get that the probability here is 0.3673. And now the last part that we want here is, remember when you go on the probability tree, we multiply the probabilities here. So that means here we have this probability already. That is the one in green. Now we have to find the probability of containing belly button fluff. So that is given to us, which is 66%. So we're going to get the probability of having an outie, and we want fluff, is equal to the probability of outie, which is 0.3673, multiplied by fluff, which is 0.66. Now we can put this in the calculator, and we should get this 1 second. If we go back all the way to menu number 1. So we have 0.3673 times 0.66. There we go. Then we get the answer, which is 0.2424, right? 4 decimal places. There we go. We have it. That is the probability for us to get an outie belly button, and we want to have fluff in our belly button. Now, if you guys can get a few different marks here. If you guys get the probability for a outie correct, which is this part over here, this is an achieved mark.
If you guys get the probability correct with the working shown, potentially one small mistake or something, you can get a merit, but getting the correct probability with everything together will actually give you guys an E mark here for this part over here. Okay, wonderful. Let's go to the next question. Very little research on the typical size of belly buttons has been undertaken. It is hypothesized that the diameter of an adult belly button, the distance across the widest point, could be modeled by a normal distribution. Okay, so we definitely have a normal distribution question now, and they're telling us the mean and the standard deviation. Why do they do that? Because those are the parameters of our distribution. So we can already write down that x has distribution normal. And remember, in brackets, put down your parameters. We have that the mean is equal to 2.05, and we have that the standard deviation is 0.9. Okay, now we've already got everything that we need for the question written down. Now let's have a look. Calculate an estimate for the probability that a randomly selected adult belly button has a diameter of at least 1.75, given that its diameter is between 1.5 and 2.0. Okay, so in this question, you might have to read this a couple of times. Feel free to pause it and think about it. Yeah, but what do we see here? We see a given fact, given that the diameter is between 1.5 and 2. Yeah, so we have given information, which is a keyword for conditional probability. Here we go. So we're going to have to go and have a look at our formula sheet. Yeah, remember we have the probability of A given B is equal to, and I don't know if I can squeeze this in, the probability of A and B, divided by the probability of the condition, which is B. So this is a formula that you guys have in your formula sheet. Right? Yeah. Okay. And now what else does the question want from us? Yeah. So we have been given information. So let's put that part into our probability part. Yeah. This is the condition here. Yeah. That's our B. Okay. So what do we actually want to find here? Yeah, it says calculate the probability that a randomly selected adult belly button has a diameter of at least 1.75. So with other words, what we are interested here is we want to find the probability that we are at least 1.75 centimeters diameter, but we are given information that we are between. So we are between 1.5 is less than x less than 2. Yeah, I guess we can put the x here in the front as well, just to make it more complete and correct. Yeah, so we want the probability that x, or a belly button size here, is more than 1.75, given it's between 1.5 and 2. So how do we use this formula now? We have to have a look. Yeah, so we're going to rewrite the probability that x is greater equal to 1.75, and at the same time it's between 1.5 and x, so 1.5 and 2. And now we divide by the probability of the condition, which is that it's between 1.5 and 2. So if we now want to solve this question, we need to find two things. We need to find the numerator and we need to find the denominator. So what have we been given about x? We've been given that it's a normal distribution. So we can have a look at these. By the way, guys, if you guys have less than equal to signs here, that is perfectly fine. Yeah. Remember, for a continuous distribution, equal signs don't matter, because for every continuous distribution, the probability that x is some value little x is equal to 0. Yeah. So it doesn't matter if you guys have those for normal distribution and for triangular distribution and uniform distribution. Yeah, they're all continuous. It does matter for Poisson and binomial distribution. Yeah. Okay, Wonderful. Now, let's have a look. We need to go to our calculator and we need to put in the values that we need. So let's check our calculator on menu, and we're going to go to stats again. And we're going to go to distribution F5, normal distribution F1. And now, guys, what are we looking for? Let's have a look at the denominator here first. We're looking between two values. Yeah. So remember, if you have a P, that is the equal part. And if you have a C, then you have the less than or less than equal part. So we're going to take the cumulative distribution, which is what C and D stands for. So we're going to use F2. And now again, make sure you're on the variable, and we're going to put in our lower and our upper. So our lower is 1.5, our upper is 2. And now we need the standard deviation, which was 0.9, and the mean was 2.05. So if we now put this into the calculator, we find the probability for the denominator here, which gives us 0.207. There we go. And now we need to find the probability of the numerator. So how can we do this? Well, let's have a look. The numerator is a logical statement. Yeah. So it's currently telling us that x has to be more than 1.75 at the same time as between those values. And sometimes it pays to just check those values to see if you can make that any easier. So let's have a look here on the site, for example. Yeah, we are in values. Sorry, I just need to extend the screen. There we go. Yeah. So we are currently from values more than 1.75 at the same time as between 1.5 and 2. So if you look at this from a standpoint of a line, a straight line, yeah, at some point we have 1.5. Yeah, that's our lowest value. Yeah, we need to be between 1.5 and 2. And at some point here we have 1.75. And what this is saying is that we need to be within these values. Okay, that's fine. That's this condition done. And the other condition is saying is that we are more than 1.75. So that means this would be this part here. More than 1.75, technically more than this, but we still have to be within the range here from 1.5 to 2. So what this is actually saying to us is that we're actually between 1.75 and 2. So we're going to just transform this from 1.75 to 2 and use that instead. So on here, I'll make a note at the top. This is the probability that x is between 1.75 less than equal to x less than 2. And again, the equal sign doesn't matter. Divided by the probability of being between 1.5 and 2. Okay, so let's get our calculator out again, and we're going to just calculate the numerator here. So same thing, everything is still set up for us. So let's go back. Hopefully the calculator works. There we go. And we're going to go to lower value, which is 1.75, and upper value is 2. Everything stays the same. So the probability for this is 0.1084. Wonderful. Okay, cool. Now we can actually get our answer here. And if we now go back to menu, start the first one, we can put this into the calculator, which is 1084 divided by 0.2073 gives us the answer of 0.5229 for decimal places, again for rounding. Yeah, so, and excuse me, now you can see the whole working out again. Yeah, so this is now our final answer. Yeah, so this question here has a lot going on with it. Yeah, you need to think about some logical parts. You need to remember conditional probability and find that in the question. So this question actually gives you an excellence if you get everything here correct. Now, if you want to make a merit, you need to write down the conditional probability with working. So this kind of statement here, with some working out of the probabilities. Yeah, so you're going to have to find like the numerator and the denominator. And for an achieved value, you just need to figure out the normal distribution, which is at least one of them is correct. So I guess if you get the numerator or the denominator here correct, that will give you guys an achieved mark. Now, in order to get the E, you actually have to also answer the next question correctly. Yeah, so there's another condition here on getting the excellence. So let's have a look at the next question here, and let's see what we can answer. Comment on the suitability of using the parameters given above for modeling the adult belly button width. So, if you guys remember the belly button width, yeah, so X is the belly button width. So, X is our random variable here, and X had a distribution normal with parameters. Mean was 2.05, if I remember correctly. Standard deviation was 0.9. You can quickly check that. Yes, that's correct. Yeah. So this was our assumption here. This is what we were told. Now it's asking us to check if this is good or if this is suitable. So remember, if we have the normal distribution, yeah, we had a very similar question earlier on with where we had to talk about the binomial distribution. Now they want us to talk about the normal distribution and the requirements. So one requirement for the normal distribution would, for example, be the range of values. Yeah, we did this in year 12 and in year 13. And all of them have been the excellence kind of questions, is that if we draw the normal distribution, wow, that actually worked out really nice. Yeah. Remember, they never go to 0. Actually, now when I look at it at the screen, it is not that perfect. But okay, it is what it is. Let me try one more time. There we go. Oh, that's even better. Okay. So remember that in the middle here, we have ourselves the mean. And then what we do is we have the mean plus a standard deviation and minus the standard deviation. We do this up to 3 times. Here we have plus 2 standard deviations, and here we have 3 standard deviations away. And you guys need to remember these by heart. Yeah, so I'll just finish this drawing. Yeah, there's certain percentages. And the percentages are that from here to here, 2 standard deviations away is 95% of the data, which is this red part over here. Yeah. If you guys have 3 standard deviations away, yeah, so from here to here, we have an even more strong condition. Yeah, so let me just move it down a bit. There we go. This is a 99% interval. So between these values, everything that's here in the middle parts, all of this is 99% of our data. So this is usually how we check if some of these are correct or if some of these work. So let's have a look. What are those values? Yeah. So the mean minus 3 standard deviations, and we want to find the mean plus 3 standard deviations. Well, the standard deviation is 0.9. Then the mean is 2.05. We're going to get minus 3 times 0.9. Hopefully is that, yeah, that's still on the video. Perfect. And then we have 2.05 plus 3 times 0.9. So let's have a look. Maybe I can go over a little bit so we can fit that on the screen for us. What numbers do we get? Let's get our calculator out. Got that? Yes. So we're going to get 2.05. minus 3 times 0.9. Oh, there we go. Which is negative 0.65. One, please. Maybe I'll just zoom out a bit. There we go. So we can all see. Perfect. And then we do the same calculation. And we're just going to go back and we're going to change it to a plus. So we have 4.75. So now we know those values. Yeah. So what does that mean? This value here is this, and we have this value here. So that that means now that we have 99% of our belly buttons
are between minus 0.65 diameter and 4.75. And remember, these are centimeters. So if we look at this now, this tells us if the normal distribution is appropriate here. And let's have a look. Well, we have a negative number. Yeah, so we have an issue here. Yeah, cannot be negative. I have never seen someone who has a negative diameter for their belly button. However, this model says it's possible. Yeah, that's one part. And also, you guys can comment on the extreme value, right? It said 4.75 centimeters. I mean, that is about this much, if I'm correct, right? I have never seen someone who's got a belly button that is that big. So according to this model, we should have that, but that's not actually true in reality. So we can comment here that the normal distribution is not appropriate. Or at least the parameters that we have are not correct. The normal distribution may be correct, yeah, but the normal distribution parameters, yeah, I'll put this parameters, there we go, in brackets, yeah. I really mean the parameters are not appropriate for the distribution. Okay, let's have a look at one different way that you guys can comment on this question, yeah. And usually I like I like to talk about negative values when I have a normal distribution, yeah. So if you guys wanted to find the probability that x is less than 0, so it's negative, yeah. How do we do that? Well, we can go onto our calculator again, and we can go to our probability distribution. We can go menu and then to stats and distribution normal. And again, NCD, it's always C, when it's always the cumulative distribution function. If you have a continuous variable, you can remember continuous variable has a C, so use NCD. And now let's have a look here. We have lower value. We're going to go with 0. And actually we want less than 0, so it's going to be negative infinity kind of, so just a really low number. And then our upper limit is 0. Again, it doesn't matter if it's equal to 0 or number just below. And the standard deviation and mean are still the same. So let's have a look. This tells us that there is the probability of 0.0137. So we roughly have 1.37% of the population who have a negative distance or a negative width for their belly button. Yeah. So this is another way that you guys can comment on the appropriateness of the model. I highly recommend that you guys remember how to do the 3 standard deviations away and what the probabilities is, because this is a lot more use, yeah, in a lot of situations. But if you guys have a real situation, always remember negative numbers don't work. So if you want to check if something is appropriate, you check the things that should not happen and check if they do. Okay. But one more thing I wanted to mention here, this probability is always going to be positive, right? There's always, according to the normal distribution, always going to be a chance that this happens because there is a asymptote here, right? It never touches the x-axis here. So when you get values here, you're looking for small values are not okay. Yeah, we want something like 0.00001 or something similar to this. Yeah, so 1.4, for example, times the 10 to the negative 5. Any of those kind of numbers would be acceptable because the probability would be so small, we wouldn't worry about it. All right, quick cut, and we're back to question 2. Sorry, I don't have that much time to do all of the questions in one go. So now we're off to another question. So let's give this question a read. It's quite long again. Fluff collects in the belly button of some people. The nature of the naval fluff study from Steinhauer. All right, we are back for question 2. Sorry, I do not have enough time to do all the questions in one go. So let's give this one a quick read. So, fluff collects in the belly buttons of some people. The nature of naval fluff study from Steinhauer was published in 2009. The author of the study collected data about his own belly button fluff each day for 502 days. Wow.
He had a morning shower where he washed his belly button, and at the end of the day, he removed and weighed the belly button fluff that had accumulated during the day. Wow, okay. But what a commitment, right? Okay, the weight distribution of the amount of the belly button lint, the fluff, he collected each day is shown in figure 2. So we have all of the frequencies of the different weights. Okay. It is proposed to model daily belly button fluff weight using a triangular distribution with the parameters minimum 0, maximum 7.4, and mode 1. Okay. Sketch the model. Okay, we just need to sketch it. Okay, so what kind of distribution do we have here? Yeah, so we can have a look. They are telling us it is a triangular distribution. Yeah, so we are looking at something like this, where we have B, A, right, and C. Yeah, C is your mode. And this is exactly what we're going to draw. So let's have a look. The question is telling us we have minimum 0. So I'm just going to zoom in a little bit, make it a little bit clearer. Minimum 0, maximum 7.4. So about here, well, it's actually the end of that little part there. And mode, which is, remember, the most common one is at 1. So that's about here. So we're going to have B, we're going to have C, and we're going to have A. And now we just need to draw a triangle that fits. So I guess we could do like something like this. Maybe I'll cut this out. There we go. Yeah, so we have ourselves a triangular distribution. We could have gone a little bit higher as well, but we don't want to go to the very highest one here maybe, because here we have now a little bit too much. Here we have some missing that kind of like maybe makes up for it. Yeah, so I guess that is all we need to just sketch it. That's the first part of our question. Let's zoom out a bit and do the second one. Using the given parameters, estimate the probability that on any given day the belly button fluff is less than 1.5. Okay, so remember when you have your probability distribution function for your triangular distribution, yeah, what we really want to know is where are the numbers, because this has all to do with where the numbers are. So we have 0, we've got 7.4, and here we have 1, exactly 1.0. Okay, so, and we are interested in 1.5 and less. So 1.5 is somewhere here. It doesn't have to be to scale. It's between those two numbers. So I'm just going to make a line here. And remember, continuous distributions, if you want a probability, so the probability that x takes on values less than 1.5, that is given by the area under the curve. So in this case, that is this part here. That is the area under the curve that we're interested in. Now, there's two ways that we can calculate this, and I will actually do both ways. Yeah. So one way is to calculate this by separating the area into two parts, which is the first area and the second area. So let's have a quick look. Area 1 is a triangle, so it's half times base times height. And the base here, well, the base here seems to be 1. And the height here is this part here, right? So if we're looking, how high is that? Well, in the formula sheet, it is given that this height part here is 2 divided by b minus a. Yeah, so we can calculate this by 2 divided by b is 7.4 minus a is 0. And let's grab a calculator real quick and chuck that in so we know what we are getting ourselves into. Back, there we go. Okay, so we're going to get 0.5, which is half, times 1. We don't really need that. And you guys can put a fraction if you guys want, whatever is easiest for you guys. Just put it in as you have it. 7.4 minus 0 is 7.4. And the answer here is going to be 10.5. No, it's 0.5, right? Yeah. So how did I realize that was wrong? Remember, this is a probability. A probability can't be 2.8. There we go. So
this is going to be 0.1351. Yeah, sorry, I've put that in there, but of course our calculator blocks it. And now the second part here is we need to find the area 2. Yeah, let's zoom in here a little bit so we can have a look. And that's right, I actually got the formula sheet here as well. Yeah, for us to have a look at it. Yeah, this is where I got all my information from. Yeah. Now, when we now look at 2 here, 2 is actually a trapezium. Yeah, so we have 2 parallel lines. We have 2 lines connecting. Yeah, so if we want to find the area of this, you're going to have to memorize the formula for a trapezium. So the formula is the side length A plus C divided by 2. So that is the side lengths here in yellow, A and C. Add those together, divide by 2. And when we multiply it by kind of like the height, but the height in this case here is how far they are apart. Yeah. So why am I going through with this question in this way? It's because sometimes for harder questions, you might need to calculate the area of the trapezium here. Yeah, we're going to see there's an easier way to answer this question, but for some parts, for example, if you wanted to do the probability that x is between 2 and 4, you would have to calculate this trapezium here, right? Which is between 2 and 4. So let's take this one out. That's not part of our question. Yeah, and now we're going to actually put in A and C. So we already know this one here, which was the same as before, which is 2 over 7.4. And the other part here, this height here, we need to still find. And remember, this formula in the formula sheet here always gives us the height. So what we need to do is we need to check where we are. So let's go and have a look at our formula sheet in detail. Yeah, whoops, there we go. Move it over here. So we know we're somewhere here. So we are between C and B. I guess AB, I kind of mixed A and B up, but it doesn't really matter. The numbers are going to be exactly the same. No, I didn't. No, that's correct. I just wrote it, I think, incorrectly on here. Yep, that's correct. So it should be A and B in this order. A, B. There we go. Sorry about that, guys. Okay, so what we're interested in here is between C and B, which is this one here. So we need to use this formula here to find the height. Yeah, this will give us the height over here, this number here. So let's go back to our formula. So we're going to chuck that in. The height here would be 2 times B, which is 7.4. minus x, and in ourselves x is 1.5. That is our value that we have, divided by b minus a, so 7.4 minus 0, multiplied by b minus c, which is 7.4 minus 1.5. Awesome. Sorry, minus 1. Gosh, what is going on today? Minus 1. Sorry guys. So how do we put that in the calculator? Check what we get for our number. So we have a fraction. Fraction. We have 2 times, and then open bracket 7.4 minus 1.5. And in the denominator, we have 7.4 minus 0. Well, that's 7.4 times 7.4 minus 1. I guess I could have done that in my head, but it's okay. Doesn't matter. We can just put it in the calculator, and we get 0.2492. So how does that help us now? Let's have a look. This is the height over here. It's getting a little bit messy. Yeah. 0.2492. Okay, now we have our A. We have our C in our formula for the trapezium. And now we're going to put all of those in. Yeah, this one here is our A. Then we're going to have our C, which is 0.2492. We're going to divide those by 2 and multiply by the difference between those two, which is 0.5. So this is very complicated and is required for the higher grades. Yeah.
But here I want you guys to see later on that there's a much easier way. You probably already figured this out and asked yourself why I'm making you guys work all this out. Yeah. This is a very common one for merit and excellence questions, to have to figure these questions out this way. So I'm not actually going to, actually, should we put this in together? Yeah, let's put this in the calculator real quick. Why not? I mean, there we go. We have a fraction. Yeah, remember, you guys are more than welcome to do a double fraction. Yeah, 2 divided by 7.4. And just put it all together, plus 0.2492. I'm going to divide by 2. And then this whole number we're going to multiply by 0.5. So we get 0.1299 for decimal places. And how do we now find the area of the whole shape? Yeah, we can now add A1 and A2 together. So A1 plus A2 is equal to, and we can do that in the calculator real quick, the answer that we had just now, plus 0.1351. So we get 0.264, 2650, right? If we have 4 decimal places. All right, so this was definitely the longer way. Yeah, and there's a much easier way, but I wanted to show you guys how to do it if you have a trapezium, because sometimes they have these questions in the exams. And sometimes when you're sitting there and you're not too sure what to do, you might just have a mind blank and you don't know how to actually answer this question. So let's go back real quick. I'm just going to make some space. I always have to make some X's here. There we go. And just real quick to do this question, yeah, we have 0, we have 7.4. 1 is the middle, so we have our distribution looking something like this, and we are interested in 1.5. Yeah, the probability of less than 1.5. I should write at least this one correct. The x takes on values less than 1.5. So how do we do this one? This is the same thing as the opposite. Yeah, minus or 1 minus the opposite, and the opposite is that x is greater than 1.5. So this is this area over here, and it's a triangle. All we need to do is base times height here. So we have 1 minus half times base times height. Well, we already figured out the height here, this number here, and let's check what that was. 0.2492. So you still have to go through this process and figure out what the probabilities are. Yeah, but now we can just multiply this number by our base. Yeah, so our base here is 7.4 minus 1.5. And if we put all that together, sorry, it's a little bit messy. There we go. We can put that in the calculator, and that should give you our answer. Hopefully it's the same number that we had before. Hopefully we didn't make any mistakes. There we go. Half times 0.2492, and we're multiplying it by the difference of 7.4 and 1.5. Is it? There we go. And our answer here is 0.2649. Is that the same number we got before? Yeah, I guess it's just a little bit different for rounding, right? Awesome. Wonderful. 2650. 2650, basically. Yeah. Awesome. Okay. So lots of practice for you guys. Yeah. Let's have a look. You guys need to get the probability distribution here correct. Yeah. So the drawing correct for an achieved mark, and getting the probability here correct will give you guys a merit either way, no matter how you guys calculate this. Yeah, but this trick here should be you guys should think about this one whenever you have your triangular distribution. Awesome. Okay, hopefully I haven't lost you guys here. I had a lot of explaining to do for that question. If you guys solved it and you went way ahead of it, that's perfectly fine. Let's have a look at our next question.
Suggest alternative parameters for the triangular distribution that will give a better fit to this data and sketch your new model. Okay, so we're actually doing a new one. As part of your answer, justify the choice of your alternative parameters. Yeah, so I actually didn't really like these parameters here because of the amount of space that we had left here, and then we kind of had to make it up for at the top to kind of not overcompensate for any area. I guess they give us freedom here to do whatever we want, and it's kind of obvious to me that like the peak should be somewhere here, right in the middle. Clearly we need to start at 0 because we can have no lint in our belly buttons. And some of these are maybe a little bit too high. There's only like a few of them in the 500 days. So the probability here, if you think about these, there's like maybe 10 or so altogether here. 10 out of the 500 are above a certain value. Yeah, so we're going to have to choose a certain value that we're going to stop. And I think just by looking at this, like somewhere around 4 is probably what we want to do. Yeah, so maybe let's do like 4. Let's do 4 because it's a nice number. And the top part, we're probably going to do in the middle. So right by 1. We could probably do a little bit before it. Yeah, just to kind of compensate for that extra part before. That's perfectly fine. So let's draw this triangular distribution here, and then hopefully I can make it look very nice. So I guess there we go. Yeah, this is now my suggested triangular distribution. And here now we have excess distribution triangular. And we're going to get parameters. So we need to give A and B, right? And C. So A, C, and B. We've given A 0, we've given B, let's do them in order, is 4, and C is equal to 1. Now, you guys would maybe do a different one, but I'm pretty sure the range of values that they are going to accepting is somewhere like between here and also somewhere between these values here. Justify this choice. Yeah, I mean, whatever I've just said, right? Because these ones here are, there's only a few here. The probability here is very low, so we're going to ignore them. Potentially, these might be outliers, right? Okay. So let's have a look. I think that's all we needed to do, right? Suggest a new model and sketch it, right? Yeah, awesome. Okay. So, completely new question, unrelated to what we had before. Kind of. So, the table, did I give you guys the marking schedule? Yeah, crazy. For this question here, actually, you guys need to have the 3 parameters correct. This will give you guys an achieved mark for the 3 parameters being correct. And if you guys also justify at least one of the parameters, yeah, so they want you to justify each of the parameters. So as I said before, if you start at 0, yeah, why do we start at 0? Because we can have no lint, right? So we definitely have to start at 0. That's a possibility. Why do I go to 4? That's because I'm going to call some of these an outlier. And why do I have C here in the middle? Yeah, that's because that is the highest point in the graph and it looks like it is the most frequent option very close by. Yeah, if you guys get at least one parameter that you guys explained together with the correct values, so one of them will give you a merit. And if you guys have all the 3 parameters, or at least 2 of them explained, but all 3 correct, that will give you guys an excellence here. Okay, so next question. The table below shows the probability distribution of a random variable t, the number of towels used for a person or per person for residents from one city over one day. Okay, so we have 6 values that t can take on. Yeah, either no towel or 6 towels or anywhere between that for one day, and different probabilities for each. How many towels on average were used by a resident from this city over the one day? Okay, so it's asking us for the average. We have a probability distribution and
you guys can have a look on the side. Yeah, if we want to find certain values like the mean or the standard deviation, there's formulas that they give us. And even though these formulas look very terrifying, all right, sorry, my recording went out. Let's just get started with the next question. We have the table below shows the probability distribution of a random variable t, which is the number of towels used per person for residents from one city over one day. So here at the top, we can see how many towels we have. So we can see someone is using either 0 or 6 or anywhere in between number of towels per day, together with the respective probability for each of those outcomes below. So now the question here is asking to get us the average amount of towels that we need. So the average is of course the mean, and if you guys want to, you guys can calculate this one by one. I would assume that you have a graphics calculator with you. So what I suggest that you do is you're just going to go and grab your calculator out and enter all the data. Now I've just actually done that, and then the recording went down. So we have all our values in the t, that's our x values from 0 all the way till 6. And on the other side, we've got the probabilities exactly as they were given to us. Now, what we're going to do in order to figure out how this is, there's a couple of things we need to keep in mind. You need to go and make sure you're setting it correctly. We're going to go F2, which is calculate, because we want to calculate things. And now we're going to get F6 and press set, just to make sure we're on the right settings. And what this is going to give us is we're going to be given different parts that we can calculate. What we care about is one variable. So the first variable, that's what we care about. That's our random variable. That's our first column. And we're going to say here that the first variable is at list 1. And the second variable is the frequency. That's the probabilities. You have to make sure you set this to list 2. So your one might be 1. Yeah. If you want to change it, you have to press list and enter the second number. So 2, because that's the second column. What this now does is it takes the second column together with the first variable when it calculates things. Now we can press F1, which is variable, and now we get our answers. So here we have our mean, that's the one with the x bar. So let's write that down. So we have the mean, which is x bar, is 2.031. And we might as well write down the standard deviation here. Standard deviation of t is equal to 1.405. Yeah, there we go. And now all the question here wanted is how many towels do we use on average in one day? And that is already given to us straight away from this question. So if we now write down the number here, that will give us an achieved mark here. All right, next part. This is our second part to this question. We have let the random variable c, now a new random variable, be the number of sets of clothes worn for residents from the city in one day. The maximum number of clothes here is 3. So that is something to note of. The maximum number is 3. And the random variable c has a standard deviation of 0.5. So that's also given to us here. And now the question is saying show that c has a lower standard deviation than t and give one reason why. So we need to make sure that we don't forget the reason. So what are we doing? We're comparing the standard deviation of c and the standard deviation of t. So the standard deviation of c is 0.5. From the question before, we have the standard deviation of t. Yeah, remember we got that from our calculator. We have that right there where we have the standard deviation sign. Yeah, so that was 1.405. 1.405. And of course, just by finding it, we can see that the standard deviation is, oh my God, what am I doing? Is larger for t. Yeah, so we have now shown that the standard deviation of c is smaller. And you can even write it like this, doesn't matter. So this all will give you your achieved mark here. We got everything with the calculator. Make sure you guys know how to put it in the calculator and change the settings if you need to, because this will make the calculations a breeze. Okay, next part. We need to give the reason why this might be. Well, let's have a look. Here, the number of towels is a number between 0 and 3. Oh, sorry, the number T, yeah, T is our towels, is a number between 0 and 6. And C, the clothes, is a number between 0 and 3. So we have a smaller range of values for our clothes. And if we have less opportunity or less range, of course, the standard deviation, or you can also say the range is smaller, the standard deviation is smaller. Yeah. So we can say that here the range is smaller, so that means the standard deviation must be smaller. Yeah, we have less opportunity to make things different. Okay, giving the reason here, referring back to the maximum being 3, will actually give you a merit mark here. We have been given that the standard deviation of T and C combined is 1.754. And the question is, are they independent? And here, all this is a little bit of algebra, but you don't need to really understand too much of what all of these expectation formulas are meaning. But what you guys need to see here is that this formula here is true if X and Y are independent. So if you guys want to get more of the higher marks, you guys need to know how this works. However, in this case, we just have the standard deviation of T. We have 1.405, if I remember correctly. We've got the standard deviation of C was 0.5. And we have the standard deviation of C and T together is 1.754. Okay. Now, this is the information that we have, and let's have a look what this expectation algebra formula actually means. It says there that the variance of something with X and something with Y, so two different ones, we're just going to ignore the number in front because we're not multiplying T by anything. We just have the random variables by themselves. A and B are non-existent, or they're 1. So we're going to get variance of X plus variance of Y. And if this is too much for you guys, just remember what the meaning of this is. Yeah, if two random variables are independent, so if we have independence, that means we can add the variances. Yeah, and I want to be very clear, it's the variances, which is the standard deviations squared. Yeah, so what the question is already telling us is that we have standard deviations, but we need to work with the variance because that's all we can work with. So we're going to calculate the variance for T, the variance for C, and the variance for C plus T. And how do we do that? Well, remember the variance is the square of the standard deviation. So we can just jump onto our calculator and we can square all those numbers, not double. There we go, times 1.405. Hopefully I'm in. Oh, it's not working again. Sorry, guys. Hello, calculator. There we go, 405. And then we're just going to do squared. Then we need 0.5 times 0.5, which is 0.25. We knew that one. And then 1.754 times 1.754. There we go. Let's put all of those values in. So for T, yeah, we had 1.9740. Very good. And for the next one, for C, we had 0.25. And for the last one, we have 3.0765. And I'm going to remove the calculator again so you guys can see. Awesome. So now all we did is we converted the standard deviation to our variance for each of these numbers by squaring them. And now we can use our formula, which says that two of those standard ones are added, and that should be the same as the other one. Well, let's see if that's the case. We're just going to go and add them together. So we're going to get 1.9740 plus 0.25. Let's have a look what that is in the calculator. Yeah, so we're going to get 1.9740 plus 0.25, which is 2.224. But for the variance, we get 3.0765, and they're clearly not the same. Yeah, so what does this mean? This means that in our formula, we've got an issue. Yeah, this means that we don't have the exact same values. Yeah, so that formula where we add the variances together and we get the combined variance doesn't work. Yeah, and if this is the case, they are dependent. Yeah. Why is that the case? Well, if two of the random variables are independent, yeah, that means they don't affect each other. That means the variance of one and the variance of the other are the only parts that affect the overall variance. But when you have two random variables that are actually dependent, we actually have a covariance as well. You guys don't need to know that one, but we actually have the variance of x and y added together is the variance of x plus the variance of y. But now we still have two of the covariance of x and y that we needed to take care of. And this is not really required for you guys, but just so you guys understand a little bit more, the covariance is the variance when x and y affect each other. Yeah. So if they don't affect each other, right, if they're independent, then this is 0, and that's why our formula works. But our formula doesn't work if they are dependent on each other, because there's a variance, the covariance, which is between x and y themselves, because they're affecting each other. Okay, let's have a look what we get here for marks. If you guys find the correct solution, that they're not the same, this is a merit, and then explaining this and saying that this is because they're not independent here or dependent, that will give you the excellence mark. Okay, wonderful. There we go. There we go. Let's go and do question 3. But again, I'll see you guys in the next one. All right, everyone, let's do question 3 of the 2024 past year paper. Let's give it a quick read. A study published in 2012 based on the data collected from 138 people participating in a nationwide American citizen science project in 2011 collected information about belly button habits, the distribution of washing frequency, defined as the number of belly button washes per 7-day week, is shown in figure 3. So we can see how often people wash their belly buttons in 1 week period. And we have a frequency table here, or a graph here. A is asking, the media releases reporting on the study's results had a following headline. Shocking news. Less than a quarter of US citizens wash their belly button daily. Comment on whether this headline is correct. So you guys just need to have a look at the graph. What is it actually showing? We have our frequency over here and the number of belly washes per week. And in the question, it's saying less than a quarter of citizens wash their belly buttons daily. So daily for our data here would be 7 times a week, right? So what we're looking for here is the probability of washing it at least 7 times a week, right? So we want our random variable to be more or equal to 7, right? Because 8 times would be more than 7, 9 times would be more than 7, right? That would be more than daily. So how can we figure this out? Well, we have a frequency here. This number here is, I don't know, maybe 32. We have maybe 32. Then maybe this one is another 1 person or maybe 2. Doesn't really matter. Yeah, it's just roughly estimates. And that is the total amount of people divided by how many there are, 138. So we have 34 over 138. So you guys can just chuck this in the calculator. You can also leave it like that if you guys know what that is as a probability, but it's easiest to comment on this by just putting it into a decimal. Let me just quickly change that. So we have 34 divided by 138, which gives us roughly 24%, 24.64%. Awesome. Now, after having this all together, this means that we are about a quarter, right? We need to comment on this and answer our question. So it's saying less than a quarter of citizens. A quarter is 25%. So less than that is 24%. So the claim is true. Getting the correct probability as well as saying that the claim is true will give you guys a achieved mark here together with the calculations. And if you guys have like 32, 33, or 35 or something like that, that's basically okay, as long as it would be reasonable to assume that is the numbers that you're looking for here. Okay, let's do the next question. Suppose the number of belly button washes per week for the general population is modeled by a Poisson distribution. Yeah, we haven't done Poisson all day today in this paper. Use the Poisson model to calculate an estimate for the probability that a randomly selected person from the general population washes their belly button at least once a day. Oh yeah, so again, be very careful. Make sure you guys read these slowly, one by part by itself. Yeah, one after the other. Here it's per day, and remember our model here is going to be per week. Always make sure you're comparing variables as you read to make sure they match. So the question wants to know the probability, and now let's have a read through again. The probability that a randomly selected person from the general public, blah blah blah, washes their belly button at least once a day. So here we have x as our random variable, is the number of washes. Yeah, which is per week. Is that still on the thing? Yes, perfect. Yeah, per week. But what we actually want is we want daily. So in order to make it daily, we can have a different random variable, right? Which is 1/7 times x, which means we just divide whatever the number is for x by 7. So for our random variable, the one that is daily, which is y. So I'll just put this here. This is daily. Yeah, number of daily washes. So y is equal to 1/7, yeah, times the number of x. So what does that mean? That means we have a new distribution for y. So it's still Poisson, but our parameters, there's only one parameter for Poisson, it changes. It is now 2.8, which is weekly, divided by 7. So if we now have this, we've got our Poisson distribution, we've got our parameter set up. Now we need a probability statement. So we want at least one per day. So at least one is this way. This is what we want to find. However, there's going to be a little bit of an issue here. Yeah, remember that when you put this into the calculator, you've got two options. Let's go to the calculator and have a look. You guys will find this when you get yourself into this position as well. Let's go to Stats menu, and we're going to go to F5 distribution, and we're going to go next to find the Poisson distribution. Remember, we have two options. Yeah, we have Poisson PD, and then we have Poisson CD, and the other one is the inverse. But let's just use these ones. This one is the probability density function. And this is the one when we have something like probability x is equal to a number. So if we have an equal sign, yeah. So if you ever wondered which one to press, that's the one where we have an equal function, an equal sign. Sorry about that. The other one is the probability, I can't spell. Probability cumulative function. So here we're going to be using the form x is less than equal to a number. So if we want to use this one here, we need to have the less than equal sign. Otherwise, we can't use the calculator. Here we need an equal sign. So let's have a look what we have here. We have the probability that y is greater or equal to 1. We can't do greater than. So we're going to have to think a little bit. Well, Poisson means we have a discrete distribution. That means the values that y can take on are 0, 1, 2, 3, 4, and so on until infinity. So we have only got whole numbers starting with 0. So here for greater than 1, including 1, that's all of these numbers. So the opposite here is everything that's left. So we have 0. And what we can do now is we can transform this probability into its opposite, which is the probability that y is equal to 0. And the thing here is now, how do we do opposites? Things that opposite each other and create the whole thing. That is 1 minus the probability. So make sure you know how to do this trick every time you have a greater or less than equal sign that you don't want. Yeah, it's always the same trick that you guys need to use. So now we just need to find the probability, which is 1 minus the probability that y takes on the value 0. And we can just go to the calculator and put that in. Now we're going to go to PD, yeah, because we have an equal sign. And make sure your first one is on variable as always. The x value is what we're interested in, or y is equal to 0. Think of this as being x, and the mean is lambda. So lambda here was 2.8 divided by 7, and you guys can just put that in. It will calculate it automatically. Press enter, and we get our probability of 0.6703. So if we now calculate 1 minus, that would be 0.3297. Yeah, 4 decimal places. So now this is going to be our answer for the question. And if you figure out this number here, then you get an achieved mark for this. And also you need to have the correct calculation for lambda. So which is this one? So there's 2 parts where you can get a marking. Sorry, I'll just clarify that. So calculating the correct number for lambda is a mark, and getting the probability here is a mark. So getting the correct lambda is an achieved, and correctly calculating the probability here is a merit mark. If you guys forgot to calculate lambda is 2.8 divided by 7, and you still got an answer for that, then you still get an achieved mark for 1 minor mistake. Awesome. Next question. To apply the distribution used in part BI, at least one assumption must be made. Identify one assumption made that may be invalid and discuss why this is the case. Okay, so these questions come every single time. You guys need to know every assumption for all of the different distributions. Yeah, so here we have the Poisson distribution. Poisson is a discrete distribution. That means we have only whole numbers. It's not continuous. So what are some of the requirements here? Yeah, we have a parameter which is 2.8 in the case before. The lambda here is the average. Yeah, remember this is the average. Yeah, and a requirement here is that the average, sorry, I'm trying to write it a little bit faster so you guys don't need to wait here. So the average is the same every week. Yeah, so if we've got different weeks, the average is always the same. What else do we have? We have, when we look at this question here, we assume random. Yeah, it's always Poisson is an average rate that something happens. Yeah, so we have a randomness. I can't even spell, sorry about that. So randomness. So the rate that we're looking at here for washing your belly button is random between people. But is it really random? And that's the question mark here. Not really, right? Because when you think about it, is it random if you're going to wash your belly button or not? Well, you think about it. If you've already washed your belly button before, it's not random when you wash it again, right? Just because you washed it 5 minutes ago doesn't mean you're going to wash it again. You're probably not going to because you've already done it. So it's not random. You don't throw a dice
every single day to figure out if you should wash your belly button. I hope so, right? Also, the next part, we assume independence. So we have independent between days, right? The washes themselves are all independent between the washes, yeah? So is that true? And again, no, right? It's not independent. If you've already washed it on one day, right, then that will affect whether you're going to wash it again or not. If you've washed it 7 times already, then that will affect whether you're going to wash it again or not, which is kind of daily, yeah? And then there's one more part that we can comment on, and that is the behavior here. So, yeah, so is it independent for the people that we're looking at? Is it the same for everyone? Is every event, so this is the event part, is every event here random or not? So if we think about this, that also doesn't make any sense, because it is not random what people do, right? We're humans, we follow patterns, we have certain structures in our homes, yeah? So we usually wash ourselves 7 times per week, which is daily, so 7 per week. And that makes sense that we have a spike of people washing their belly buttons 7 times a week, because what we have is someone taking a shower every single day. Yeah, this is exactly what we have here in the graph. We have some people never washing their belly button, so they basically don't do it at all, or maybe they don't do it when they have a shower. But then we have a spike here, which is people that are washing their belly buttons every single day when they have a shower 7 times a week. Okay, now any of those parts here, you guys can comment on, and you guys are required to have 1, yeah, in order to get the mark. Explaining why they may or may not work is also part of the requirement, yeah, and if you identify just one of them, you get a merit mark here. And remember, for all of these questions, it's always the same. Think about independence, think about the parameter that you've been given, the situation as a whole, yeah? So do these things that we need for a Poisson distribution, do they stay the same? Okay. Now, for the next question, yeah, we're almost done. We've got 2 more question parts to go, I think. Yep, that's it. So here we have the sample data shown in figure 3a is run through a simulation model 1,000 times. Assuming that a Poisson distribution with lambda is 2.8 is used to model the number of belly button washes per 7-day week for the general population. Figure 3 shows the results of simulation model and the original observed data, which is the blue dots. Yeah, so we have the same data as before. Now they want us to explain what the gray band is showing in figure 3b. So that's these parts here. What does that show? So there's a couple of things that we need to talk about here. And one part here is this is the 1,000 resamples that we have using the Poisson distribution. Yeah, so we're going to have each line. So each line is 1 resample. Are we still on the page? Yeah, very good. Okay, and we need to kind of talk about this as this being the expected outcome. Yeah, so this is the expected outcome. Under the Poisson distribution, of course, with lambda 2.8. So if lambda is 2.8, we model, we go through what would happen, then one of those lines here is what we would expect, that specific sample. And again, of course, we sample with n is 130. Where's the number? Was it in the question before? We had a number of how many we had. 138 people. Yeah. Where are we here? 138. So the first part here is that is the expected outcome. That's what we expect. We simulate something and then we do it over and over and over to kind of see what we have. The second thing that you guys need to talk about here is that we
Why do we do it 1,000 times and not just once? Yeah, we do it 1,000 times because we want to see the variation. Yeah, variation between resamples. Let's see if I might quickly disappear here so we can put more on the screen. Okay, so we have our variation. We want to see how much is the difference between these. So you can kind of see here our answers or our population, our resample data here is kind of between these values. So this here is our difference each time. So that kind of shows us the variation. If it's very large or it's far apart from each other, those gray lines, that means we have a lot of variation. Here we can kind of see we're expecting anything between those lines. Now, for these frequencies, yeah, that the up and down kind of movement, that is the general kind of form that our Poisson distribution is going to take on. And in order to explain what the gray part here is, we can get 2 marks. If we talk about one of those two things, one of those two, then we're going to get an achieved. If we talk about both, we get a merit here. Yeah. So remember here, the way that you can realize where the marks are is to talk about why we do it 1,000 times and why do we do a resample anyway. Yeah. Basically explaining here what each line is and why we do it. Okay. Next question, we have based on the results on the simulated model and the original observed data in figure 3, discuss whether the Poisson distribution model appears to be inappropriate for modeling the number of belly button washes per 7-day week. So this is a straight up very easy solution here. Well, the gray is what we would expect if we have a Poisson distribution with parameter 2.8, the mean 2.8. And that would make sense that there's a spike here because 2.8 is our mean, right? That's our average. So we would expect more to be in the middle. So what we're going to have to talk about here is that the endpoints don't match and the middle point doesn't match, and we can just compare the shapes visually. So the first mark here we have visually. Yeah, so the endpoints do not match. Do not match. And of course, I would expect that you guys write it a little bit better than me. So you would have to give evidence. So for example, for 0 washes, right? The frequency is, I don't know, and you guys can have a look here, is about 51 of, 51. So we have the probability of 0 washes is about 50 or whatever, 51 over 138, maybe 52. Yeah, it doesn't quite matter as long as, of course, your number matches, right? But for our sample, or 1,000 samples, I should probably say. But for our 1,000 resamples, it is very low. Sorry, I'm just trying to write rather fast. I probably just want to talk to you guys about it, and you guys can put it in words yourselves, right? To write it down. So one part here is to talk about it visually. Yeah, so the endpoints don't match, and then also the midpoints. Yeah. Well, we're talking here about the average mark. Yeah, so where we have the sample mean, which is about 2.8. Yeah, so we have a spike in the resample, but we actually don't have that spike at all in our previous, in our frequency table. Okay, now, if you guys want to get a mark here, there's a lot of options here for you guys to get marks. Just saying that it is not supported, it's not good by any reason will give you guys an achieved. And I'll just say one reason or something, and saying no will give you guys an achieved mark. In order for you guys to get a merit mark, you need to comment on it a little bit more carefully by visually comparing some parts. Yeah. So you have to have specific evidence, which we said here are the endpoints and the midpoints, and comparing them with some numbers, so numerical evidence. This will give you guys a merit mark. And if you guys want to get an excellence here, you also need to talk about the sampling variation and what you would expect by chance alone. So let's have a look here. If we had variation, yeah, we talked about that before, the band, the width of the band, that would mean that we are somewhere between them. Yeah. So for the E mark here, let me go over here. So for the E mark, you guys need to add that there is variation within the resamples, but we expect to be within the band, right? And because of sampling variability, sorry guys, I'll just move it over here like this. Yeah, because of the difference in variation, we would still expect to be within that band, but we're not. And it is very important for you guys to mention, yeah, that the variation, or that the 1000 samples comes from chance alone. Yeah, so this is the part where we have just randomness. Yeah, remember how we said that one of our assumption is that we have randomness. It's completely random how many washes we have. That's not the case. And that's why here our random number, our Poisson distribution model, which assumes randomness, does not fit our habitual body washes at all. Awesome, wonderful. The final question of the paper, which also can get you guys an E here, will get you guys to go and find an alternative model that you think is appropriate for the 7-day week washes. So let's have another quick look at it before. Let's go right up to the top. Where's the first one there? How could we in any way use a distribution here? First of all, normal distribution and normal distribution is out, right? Clearly here we have high points on the ends and there's not a bell-shaped curve. What other distributions do you guys know? We know the uniform distribution, which is kind of like a rectangle. We could think about this, but we have errors here in the beginning and in the end. What else do we have? We can have a triangular distribution, so maybe something like this. But then again, we have some issues here. There's two ways that you guys can answer this question. Oh, binomial doesn't work, right? Because we don't have a number of trials, right? And we don't have a probability of success. So our parameters and assumptions aren't met. So if you guys want to, you guys can use the uniform distribution here and just say, well, we can kind of use this one. It's still going to be a little bit off, but then you just have to find the values. So we're going to start with 0 and we're going to go to about 7 or 8, right? And then we also need to find the height of this, which, I mean, you guys can have a look at it. What do you guys kind of think? Maybe about 25 or so. So with all the information, we can kind of put things together to see what we need here for our distribution. Yeah. Remember, if you guys choose to go this path, to grab your formula sheet and go and have a look at the uniform distribution here. Make sure that you meet all the points and get the correct values. Write down X has distribution uniform, put down your values. I want to do a little bit of a different thing here because I don't think any of our distributions really fits well. According to the marking schedule, you're allowed to use the uniform distribution here. And I'll just quickly blend this in. Sorry, I can't blend this in right now. But just like I said, find the numbers that you've got. A has to be like 0, that's the start. B has to be between 7 and 9, depending on where you want to go. And then you go from there and build your distribution. If you want to now comment on this, yeah, remember, just make your point. I think it is all the same across the week, except from one there's a bit higher where it's a bit lower. So it's kind of evening it out. And you can say it's still not perfect, but it's better than the Poisson distribution, which completely has the opposites, where it goes up and where we have the most frequent uses. So now
I want to actually do a question where we actually create our own distribution a little bit differently. We're going to kind of like hard code this one and tell the user what our distribution is. And what we can do here is that we can kind of generalize 3 different parts here. One part here is this, where we have a very, very high amount of people not washing their belly button at all. The most common one after that is 7. And then all the others seem to be around about the middle part, around about here. So let's have a look here. What's the average across this group here from 1 to 6? So from 1 to 6, we're kind of looking at, let's say 10, right? So we have about 10. And then for 7, we have, let's say, about 32. And for 0, we've got about 51. Yeah, so just that's like kind of an average to have a look at how many we have. So let's build ourselves a little model, and we're kind of hard coding what the distribution is going to look like. So we're going to write now. A is our random variable here, our alternative random variable. And we're going to say this has distribution, but we can't put this in here, right? So we have to kind of tell the reader what A is. So A is the number of belly button washes per 7-day week, per 7 days, right? So this is what A stands for. It's a random variable. And now we're going to give a distribution exactly how we want it. And you can kind of see this kind of thing that we have for the triangular distribution, where we have different formulas for different areas or different values. We're going to do exactly the same thing. So we're going to have the value of 0, or we can also use little a here. It doesn't really matter, just to match the number. If we have 0 washes, then we get a probability. Then for A be between 1 and I think it was 6. So 1 less than A less than 6. And we're going to include 6. So we're going to include 1. So that all of our numbers are included. We've started at 0. We've done that. From 1 to 6, included is done. Then the last one is going to be above 6. So we're going to actually go A is 7. And we're not going to allow any other number between 0 and 7 and outside that range. So if we have A is equal to 0, that would be 51 over 138. That is a hard-coded probability that we have for this. For 1 to 6, we're going to have 10 over 138 because each of those is about 10. And we're just assuming that they're all constant the same time for all of those different values for A. And for number 7, we had, I think it was 32 over 138. I think it's 32 that we said. So these are now our probabilities. Now, the only thing here that we need to kind of be sure of is that they add to 1, right? And what we can do here is we can just add them together. So let me open my calculator. There we go. And we're going to go to our normal menu. And they're not going to just randomly add to the correct number, right? So we have 51 over 135. Plus 10 over 138, sorry. So we have 51, we have 10, and we have 32. And they should add to 138, so we're missing some, right? But then 10 is for each of these numbers, So we have 1, 2, 3, 4, 5, and 6. So in total, we have 6 numbers that have each frequency of 10. That's what we're assuming. So we're going to have to add 5 times 10 more to this, and we have 143. We are a little bit over. You can also just add these together, and you're going to see they're not 1. So we just have to adjust our probability slightly to make that work. So how can we make sure that this is? Well, we are at the moment, we're a little bit over. We have 5 too much. So we can just use the probability that we've collected from this and just make sure that the numbers match. Do I think any of those are incorrect? And I think the one with 10 might be incorrect. So how many did we say we have too much? We have 3. We have 5 too much, right?
So accounting for that, maybe we just say that the middle number here is 9. If we say that there's 9. So what would that mean? That would mean we have 51 plus 6 times 9 plus 32. Now we have 137. So we're missing 1. Maybe we got the number incorrect for this one here. Maybe that is 33. And now we would have a total of probability 1. If you guys wanted to, you guys could also add the numbers together that we previously had here and then allow A is 9. Because technically that was the one that we had where we had 9 here and just set that really small probability to this. But that wouldn't really make sense and I wouldn't really recommend it because technically this is just because we have a sample that we don't have 8, right? So that's why I adjusted the numbers slightly to make them match using our frequencies that are provided. And there's just one more thing that we need to tell the reader here if we have a probability density function, so we have a model, is that the probability is 0 for any other value. Yeah, so, and this is exactly like the probability distribution for the triangular one, where you have different inputs or different domains. And for each, you've got a different probability formula or probability number. And then for any other value, we have probability 0. So this would be the preferred way to really show that you understand how these conditional or these part distributions work. And again, how are we going to justify this? We're going to write, well, we've chosen exactly what we talked about. Why do we choose from 1 to 6? Why did we choose 9 here as the average? Yeah. And so on. Making this fit the values very well means that we're able to make a much more closely related model. Yeah. And if you guys identified any other model, so if you say any other model similar to this or the uniform model, you guys get an achieved mark. And if you guys get the parameters, yeah, you give the parameters and also explain one thing about it, then you guys get a merit, explaining in depth why you do everything and getting a distribution here that kind of makes sense. So if you say binomial, of course, there's no mark. If you say normal, it's no mark. Yeah. If you say it's a uniform distribution, but it still doesn't fit quite well, and then give the parameters, that would be an E, right? And explain why you still did it and where it might not suit very well. Awesome, very good. Now these explain kind of situation, these explain marks are usually always hard, but just think about what these things mean and did you kind of say the same as what we did here? Yeah, and you can kind of justify whether you get the mark or not. Awesome, this completes our 2024 paper. Now, if you guys followed through all the way here, thank you very much. Make sure you like and subscribe for more, and I will see you guys in the next video. Bye-bye.